Okay, so hi everyone. I'm Sagie Gadasi from the laser group of Nir Davidson in the Weizmann Institute of Science in Israel. And today I will tell you about one of our recent projects in which we generate chiral state in a network of oscillators by using a complex potential. Now, in this case, this is a network of lasers. This is a laser array. And the complex potential is actually a modulation of loss and frequency detuning across the array. On the bottom, you can see a drawing of our experimental setup, which I won't go into its details because of the short time and because it's not really necessary for understanding the physics. Okay, so thanks to Kane, we'll know very good what is chiral object. It is everywhere, and it's a fundamental, of course, property of nature. And usually in physical system, if one wants to generate chiral state, it will use some kind of asymmetric coupling, like the magnetic field in the quantum Hall effect, like the artificial gauge field in the recently demonstrated topological insulator laser, or other types of asymmetric coupling. And here the intuition is very clear, right? If you have asymmetric coupling, you have directionality and therefore chirality if you have a closed loop. However, there are systems in which asymmetric coupling is not available or very difficult to implement, like, for example, our symmetrically coupled lasers. So here in this work, I will show you that we can, by using an on-site complex potential, we can generate these chiral states. Now, since it is on-site, it is very easy to implement. It can also be relatively easily transferred to other physical systems, and it can be applied to various network geometries. Here we chose the triangular lattice, and it is also scalable. Okay, so now let's understand, before we get to many lasers, let's understand the behavior of only a few. Our lasers are coupled by dissipative and negative coupling. The dissipative means that the loss of the system depends on the relative phases between the lasers. And when we turn on the lasers, they will choose the minimal loss mode. Negative means that the minimal loss mode is the out of phase when they have a pi phase difference between each other, like is illustrated by these red arrows. So now let's add a third laser. Now, this third laser is unhappy because it wants to be out of phase from both the other lasers. So now the minimal loss mode is actually when they all compromise on 120 degrees relative phase, which is just the vortex mode. However, this is not the only minimal loss mode. We have also the anti-vortex mode, where the relative phase is minus 120 degrees. So now we have a degenerate minimal loss mode. I can use the same arguments to convince you that if I have a triangular lattice of lasers that are negatively coupled, we have, again, a degenerate minimal loss mode, which are the staggered vortex and the staggered anti-vortex, where in the staggered vortex, all the triangles that point up have a vortex mode. The phase rotates clockwise, and in the anti-vortex, it's the opposite. So every time I will turn on the system, I will get one of these modes with equal probability, and therefore I will say that I have no chirality on average. And indeed, when we go to the lab and we take this triangular lattice of 250 lasers, which are negatively coupled, this is the intensity distribution of the lasers, and they also measure their far field, their interference at infinity. And now this gives me information about the relative phases, or the far field encodes the chirality. So every time that the lasers lays in the staggered vortex mode, I get these 3 peaks. Every time that the laser is in the staggered anti-vortex mode, I get these 3 peaks. So I can, from the far field, understand what is the chirality of the system. The reason that you see both vortex and anti-vortex peak is because this is the ensemble average over many realizations. And you can see that since so I define chirality as the difference in the intensity of these peaks divided by their sum. And you can see that if I have a triangular lattice of identical lasers, I have no chirality on average. So now let's understand the idea of a complex potential and the intuition behind it, so why we chose it. Here I draw an illustration of our 250 lasers, and here I zoom in on one unit cell. On the bottom, you can see the effective Hamiltonian, the traceless effective Hamiltonian that describes the dynamic of the system. You can see that the zeros on the diagonal indicate that the lasers are identical, and the off-diagonal imaginary entries means that we have a dissipative coupling. So now you understand what you're seeing here. The first thing that we're going to do is to add detuning between 2 lasers in each unit cell. Now, it is very well known in physics of synchronization that if I have 2 oscillators that are frequency detuned the phase will oscillate with a phase difference that is dictated by the detuning. So naively, we expect that detuning might insert directionality to the system and therefore chirality. However, it turns out that since the lasers are coupled both directly and both indirectly through the third laser, the two contributions cancel each other out, and therefore we get no net chirality. So we suggested to weaken a bit the indirect link by adding a weak loss to the third laser. This is supposed to restore the chirality. The detuning and loss that we added are indicated by these imaginary and real terms on the diagonal, and therefore the term complex potential. So this is the intuition or the heuristic explanation for why we think that, why we thought that complex potential will introduce chirality. So we went to the lab, and now let's make the experiment. I take each, in each triangle in this triangular lattice, I take one of the lasers, I add loss to it, and then I scan the detuning between the other two lasers. And these are the results. The chirality as a function of the detuning that I scan, and you can see that if I have no detuning, I get no chirality. Increasing the detuning to the point where it approximately equals the loss gives me nearly pure chiral states. And if I switch the direction of the detuning, I switch the chirality. Now, to test our intuition, we can now, instead of weakening the indirect link, let's make it stronger by adding gain to each third laser. When we do it, we get the exact same behavior, just flipped. If I had no loss and no gain and only scanned the detuning, as I promised you, I get no significant detuning, except this small bump that I cannot explain later if you will ask. So these three lines are actually three cross-sections of a larger two-dimensional scan. Here on the vertical axis, this is the detuning, and this on the horizontal is the loss. And you can see that, that if I only change the detuning or only change the loss, I don't get chirality. By the way, strong colors mean strong chirality, white color mean no chirality. So I must use a complex potential, and I must combine the loss and the detuning, and only then I will get chirality. And actually, the chirality is strongest when the detuning equals the loss, or approximately equals. So now let's understand it a bit more quantitatively. To do that, I take this effective Hamiltonian, I look at the minimal loss eigenmode, and here I draw the chirality of this minimal loss eigenmode. And you can see that it really resembles the experiment. I get no chirality when there is no detuning, and I get maximal chirality at a certain point where the detuning approximately equals the loss, and then I get a decrease. Okay, so these 2 points of pure chiral states are actually special points. These are exceptional points. These are special non-Hermitian degeneracies at which two of the eigenmodes of this Hamiltonian become identical, not only in their value, but also they themselves become parallel. So at the exceptional point, the system actually collapses into the vortex mode in one case and to the anti-vortex mode in the other case. So this is the only available state of the system. You can also see that these peaks are very sharp. Any small deviation of the complex potential from the correct value will just kick us out of this chiral state, which different from the experiment where the peaks are much broader and small deviation won't change the chirality by much. And the reason for that is while our analysis here is linear, the system, the lasers are inherently nonlinear creatures. And the correct thing to look at is not the loss that we add, but actually the effective loss, which is defined by the difference, by the linear loss that we put in, minus the difference in the nonlinear gain. And by using simulations, we understood that the effective loss, the nonlinear gain always changes the effective loss such that it will, such that the system will get to the exceptional point that is defined by the detuning. So we set a detuning, we add specific loss, and then the nonlinear gain will take us to the exceptional point. So we show that the nonlinearity actually pulls the system towards the exceptional point. Now, since this slide is summarized everything, I will just change the title and call it a summary. So I showed you that if I have a symmetrically coupled oscillators or lasers, I can generate chiral states by using an on-site complex potential, and I get pure chiral states at the exceptional point. And thanks to the nonlinearity, the system pulls the system to the nonlinearity pulls the system to the exceptional points, making these chiral states very robust to perturbation in or noises in the complex potential. So that's it. Thank you.
Hey, thanks for the talk. Very interesting. So I have actually two questions. First is like, how do you make those laser arrays? What kind of lasers?
Yeah. Okay. Great question. So this system is actually a degenerate cavity. It is made of two lenses and two mirrors in a 4F configuration, which allows us to generate. One of the mirrors is replaced by a spatial light modulator, as you can see here, and this allows us to generate any laser geometry that we want, any laser array geometry that we want, and it also allows us to control the loss and the tuning of each of the lasers very accurately. By the way, the first digital laser was made by Andrew Forbes group, and so this allows us to control everything very accurately, and that's it basically. This system is some kind of a laser simulator because we can simulate any laser array and control all the parameters very accurately.
Second question, could you go to the slide where you show the 3D plot of the chirality versus the
this?
Yeah, this one. Could you explain a little bit about why, if you look at the left figure, why is there like a little, like have a non-zero chirality of the red curve when the delta omega is 0?
Yes. Yeah. So I will go back to the experimental setup drawing, and I just say that this system is not entirely symmetrical. All the coupling is done here actually in between, and since I have an SLM on one side and a gain medium on one side, on the other side, then it's not totally symmetrical. And if I have any small misalignment in the cavity, it will prefer one chirality over the other, but it is uncontrollable. I cannot really use it as a method to control the chirality. Just because here the lasers on this side, I cut the lasers into these nice holes, and in this side I have this maybe some kind of non-linear coupling that I cannot control. Okay. So the fact that I have two sides and I couple them in between make this.
Thanks a lot. Thanks. Okay.
Does it work? Okay.
Yes.
So thank you for this very amazing talk. I have two questions about exceptional points.
Yes.
So first is, there is also this chirality effect associated to orbiting around an exceptional point. And so are you?
No, I didn't. It's different. It's totally different chirality.
Okay.
Right. And I didn't try to circle, and I have no dynamics effect in our system. Everything that you see is in steady state.
Yeah.
So I cannot really encircle it dynamically.
Okay.
Yeah.
And then I have the second question is, so if you change the structure of your lattice, would you be able to basically have, let's say, exceptional points of higher order, so like second degree, third degree order of, because you have a free level, let's say Hamiltonian, right? Free by free Hamiltonian. And so you have free states. So if you would add, let's say, change the lattice, could you somehow then, or could you speculate then the resulting exceptional points?
I guess
that have additional features, or?
I guess that if you will have a larger unit cell, you can really achieve this. But the higher order, the exceptional points, it's the more difficult to reach it, right? It's everything is much upper and much more sensitive. So it's a question whether it's reachable and whether the nonlinearity will help us also in this case.
Okay.
So I'm not really sure.
Okay. Thank you.
Thank you.
Take the last question.
It's very interesting talk. So my question is, your triangular system reminds me of frustrating magnetic system. So do you expect something like topological spin texture, like Skyrmion or something like that?
It's a good question. I'm not sure about the topological nature of this system. It's certainly a direction that we want to look or to pursue. So I have no smart answer about some topological invariants or edge states. Skyrmions, I'm not sure that we can see in such a system. But we really use this system as an XY spin simulator in some regime, and we have works on it. So I cannot, that's all I can say. Thanks.
All right, so let's take.
Thank you.